Hello, my name is Siddesh Patil and I am explaining the integrator circuit today. So integrator circuit is a basic circuit which is used to perform the mathematical task of integration on the input signal. So here we are using the op-amp, the resistor and a capacitor to use the integrating circuit. So the op-amp has two input signals, two input terminals, the inverting one and a non-inverting one, and one output terminal. So what op-amp does is it amplifies the voltage difference between the two input terminals. So in the integrating circuit, the input signal is connected to the inverting input terminal via resistor, and the capacitor is connected between the inverting terminal and the output terminal as a feedback. The the non-inverting terminal is connected to the ground, and the output voltage we are getting is proportional to the integral of the input voltage. So the precisely what we are getting is -1 by RC integral of V input dt from 0 to time t, which we are measuring. So the minus sign is coming because of 180-degree phase shift. So here, as you can see, the integrator circuit which we have made, the resistor which we are using is 1 kilo ohm, and the capacitor which we are using is 100 nanofarad. So here, as you can see, the red wire is the input voltage that we are getting, and it is connected to the inverting terminal of the op-amp via the 1 kilo ohm resistor. The output terminal of the op-amp is connected here, and it is connected to the inverting terminal via the 100 nanofarad capacitor. The black wire is plus VCC and the red wire is minus VCC, which is plus 12 volt and minus 12 volt respectively. This line is grounded, and we are connecting the non-inverting input terminal of the op-amp to the ground. So here you can see the Bode plot for the integrator circuit. On x-axis we have the frequency in log scale in hertz, and on y-axis we have the dB gain. As you can see in the graph, we have dB gain of 26.71 at frequency 10 Hz, while at higher frequencies such as 10,000, the dB gain is very less. That means in the integrator circuit, the dB gain at lower frequencies is very high. That means at lower frequencies we have a high amplification. At higher frequencies we have attenuation. So from this graph we can conclude that the integrator circuit is a low pass filter.
I am Pawan Sekar, and I am going to explain the basic differentiator circuit. And differentiator circuit, it is a fundamental component in electronics which is designed to perform the mathematical operations of differentiation on an input signal. The circuit is commonly implemented using its operational amplifier and a capacitor and a resistor. The op-amp has two input terminals, inverting and non-inverting, and one output terminal. The op-amp amplifies the voltage difference between the two inputs, and the inverting input is connected to the input signal source via a capacitor, and a resistor is connected between the two outputs, and the inverting input of the op-amp as a feedback. The output voltage is proportional to the differentiation of input voltage. This is the input wire which we have taken from the signal generator of 1 volt 2 kilohertz, and this is the 100 nanofarad capacitor connected in series with input, and this is the 1 ohm resistor connected from the output to inverting terminal, and the non-inverting terminal is here. It is grounded, and which you have taken the wire from input and also from output of the DSO to observe the output and input. Here is the plus VCC, and plus 12 volts, and here is minus VCC, minus 12 volts taken as power supply, and here are the common ground taken from the power supply. So here is the Bode plot for differentiator circuit. As we can see that for the dB gain is about 16 for lower 11,000, while the dB gain is negative at lower frequency,
That means we have high amplification at higher frequency, at attenuation at lower frequency, and we can conclude that the differentiator circuit is high pass filter.
My name is Pavitra Chalwani and I am here to explain question number 3, the average amplifier. As like the circuit that we have designed over here is, we have taken two amplifiers. One is an adder amplifier and one is a buffer with gain half. So here, as you can see, we have taken a 1 volt peak to peak 1 kilohertz signal, and here 0.5 volt peak to peak 3 kilohertz signal with resistors in mention R1, 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 R2 and R1, where R1 is 10 kilo ohm and R2 is 20 kilo ohm. Here the gain would be 1, so it would act as a unity gain adder. And here we have taken R2 20 and R1 as 10, so the gain would be half, as R1 by R2 is half, so it would be a buffer amplifier with gain half. And as you know that buffer amplifier helps to and the buffer amplifier, as you know, helps in isolating the input circuit from the output circuit, and it also helps in signal isolation. Now this is the circuit which we have explained earlier. As you can see here, we have taken 1 volt peak to peak 1 kilohertz signal, and over here a 0.5 volt peak to peak 3 kilohertz signal. So now, since the average is 1 plus 0.5, 1.5 divided by 2, almost 0.75 volt peak to peak. As you can see, the output signal which we are getting over here is giving a peak to peak voltage of around 750, 650 or 750 millivolt, which is around 0.75 volt peak to peak, which tells us that the input which we have taken, that is 1 volt peak to peak and 0.5 volt peak to peak, gets averaged, and hence the circuit we have designed is completely accurate and correct.